Hello everyone. Today we are going to discuss graph data structures. Let us understand this with the help of an example. So here we are taking abbreviations of important cities in the beautiful country of India. H for Hyderabad, G for Guntur, C for Chennai, V for Vijayawada. Suppose we have to travel from Hyderabad to Chennai. We can travel via Guntur or we can travel via Vijayawada, or there could be a direct route from Hyderabad to Chennai. Such a diagram is known as graph. Here, G, H, V, and C are called as nodes or vertices. The links connecting the nodes, for example, between G and C, we have a connection. This link is called as edges. Now let us look at the definition for graph. So graph is a non-linear data structure. If you see, usually the places are not all in a same straight line. Like below Guntur, you could have Vijayawada. Left of Chennai, you could have Hyderabad. Left of Hyderabad, you could have some other city. Hence, you have the term non-linear. And what is the graph consists of? It consists of nodes called vertices and links called edges. You know very well that a function can be represented by f of x comma y. Likewise, a graph is simply a combination of vertices and edges. So, a graph can be represented by g of v comma e. There are two main representations of graph. One is called adjacency matrix representation. The other is adjacency list representation. Let us understand adjacency matrix representation. For your convenience, the same above graph is shown at the bottom right of the screen. So here, if you see, what are the links that are connected from H? From H, we have three links going to G, B, and C. So wherever we have links, we will put one. Where we don't have links, we put zeros. So from H, we have links going to G, V, C. So those places we are putting ones. From H to itself, there is no link. Hence, we have zeros. Likewise is the case for other nodes. From G to itself, there is no link. From V to itself, there is no link. From C to itself, there is no link. Hence, for this given diagram, all the diagonal elements are zeros. Let us look at the connections for G. G is connected to H and C. So, take the row labeled G and corresponding towards H, you put a 1, and the corresponding column for C, you put a 1. Remaining places, we enter zeros. Let us look at V. V is connected to H and C. So here we have a 1, and then here we have a 1. C is connected to G, H, and V. So C connected to H, we are putting a 1 here. C connected to G, so we are putting a 1 here. And C connected to V, we are putting a 1 here. Such a representation is known as adjacency matrix representation. Let us look at the other representation, which is adjacency list representation of a graph. So, this is based on the linked list representation. Now here Hyderabad is linked to Guntur, Chennai, and Vijayawada. Hence, we are listing it like this. H is linked to Guntur, okay, Vijayawada, Chennai. That's the end, we are putting a null. Likewise, if you look at the graph given at the bottom right of the screen, G is linked only to two places according to the graph. One is H and another is C. So G is linked to H and C. We are putting a null because that's all. G is linked only to two elements. V is linked to H and C. So V linked to H and C. That's it. We are putting a null. C is linked to H, G, and V according to the graph given here. So based on that, we have C linked to H, G, V, and then we are putting a null. So this is the adjacency list representation of the given graph. Here, the adjacency list representation is preferred for sparse graph. Means if a graph has fewer number of edges, then we prefer the adjacency list representation. Otherwise, what happens? More number of links connected, the length of the links increase. We have too many nodes in the linked list or adjacency list representation. Whereas otherwise, that is, if the matrices consist, if the graph consists of too many links, then we go for adjacency matrix representation. First of all, why do we need such representations? This is because computer can process numbers. How does a computer process the graphs diagrammatically? It cannot. So that is the reason we are giving the adjacency matrix. A matrix representation a computer can process easily. Also, those of you who are familiar with linked list, you know very well that you can write a high-level language program and the computer can process such a program, and hence the linked list representation of a graph is easily processed by a computer. Let us look at the applications of graph. Based on the given example, I hope it is clear that an important application of graph is Google Maps. Google Maps is based on graph theory. The edges are the roads, the interconnections or the important cities are the vertices. Likewise, Facebook is another application of graph. Here, the vertices are the friends, or for example, a user is considered as a vertex. The friendship between two users is represented by an edge. Edge represents the friendship between two users. The example of GHCV or Facebook, such an example is known as undirected graph, because whenever we say two people are friends, if you say A is friend of B, then it also means that B is friend of A. And we also have other categories, that is directed graph. World Wide Web is an application of graph, and such an application is directed graph. Let us say we have page A, and inside page A, we have a link which takes us to page B. It doesn't mean that page B should have a link back to A. Such an example is the directed graph. Now let us discuss the space complexity of adjacency matrix representation. If we have 4 nodes, then we have 4 rows and 4 columns. A total number of 16 values. How are we getting 16? 4 into 4. So if we have a V number of vertices, then the space complexity is of the order of V square. The space complexity is of the order of V square when we consider the adjacency matrix representation. Now let us find the space complexity for the case of adjacency list representation. First, let us count all the nodes given in the adjacency list representation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have total 14 nodes for the given graph with 4 vertices. So let us see how we are getting 14 from the 4. If you count the number of edges in the graph given here at the bottom right, we have one edge from H to G, G to C, H to C, H to B, V to C. Total 5 edges we have. So how are we getting 14? 4 plus 2 into 5 is giving us the value 14. So 4 plus 2 into 5. What is 4? 4 is number of vertices. What is 5? 5 edges. So in general, the space complexity is order of V plus 2E is of the order of V plus 2E for the case of undirected graph. So the space complexity is of the order of V plus 2E for undirected graph when we consider the adjacency list representation. However, for a unidirectional graph, it is order of V plus E because in the case of unidirection, if you have a link from A to B, you don't have a link back from B to A. Hence, it is single E, whereas for the bidirectional graph, we have 2E, where V represents number of vertices and E represents number of edges. Thank you.